Hi, class. Happy Friday, and I bet you're glad the test is over. I know. It's kind of nice not to have a test on a Friday. Anyway, let's get started. This is the fundamental counting principle, permutations, and combinations lesson. So what we're going to do is I'm going to introduce you to first the fundamental counting principle, then we're going to talk about permutations, and then lastly combinations. And we're going to talk about the formulas that both of those have, and hopefully you'll be able to apply those by the end of the period. Okay. First thing we're going to do is talk about the fundamental counting principle, and that basically says that if you have m ways of doing one thing and n ways of doing another, then there's m times n ways of doing both. So this is kind of interesting. It's an excellent way to find the number of ways to accomplish two tasks. For example, if I own 4 shirts and 2 pairs of pants, how many different outfits could I possibly come up with? And I could do this the long way, and I could actually go, okay, this shirt with those pants and those with those, that's 2. And then that's 3, 4, 5, 6, 7, and 8. Or I could say, well, I have 4 shirts and 2 pants, and therefore I've got 8 different outfits that I could wear. So again, the fundamental counting principle basically says if I have n choices and m choices for the second task and for the first task, I just multiply those together, and that gives me all the possible choices. So if I had an ice cream store that offered 20 different flavors and had 3 types of cones, how many different ice cream cones can I make? Of course, I'm not going to be setting up each one and trying to set it with each of the different types of cones. I'm just going to go 20 times 3, which is 60. So I have different types. I've got 60 different ice cream cones that I can make. Another example is I have how many different sandwiches can I make? A deli has 6 types of meat. I've got 4 types of cheese and 3 types of bread. So how many different sandwiches can I make? I'm going to multiply those together. I've got 6 times 4 and 3 times 3 types of cheeses. And what 6 times 4 is 24 times 3? 72. Okay. So this is a deli that offers ham, turkey, roast beef, and pastrami, along with 3 types of bread, white wheat and rye. So they want to know how many different sandwiches are possible. Well, we've got 4 types of meat, 3 types of bread. So we have 4 types of meat. We have 3 types of bread. And let's see. Well, what's that? 12? That's what I've got. So this is just another way. And I don't know what this is down here, but let's see what's behind there. Oh, okay. And so that's how many types of sandwiches I can have. And this is just the fundamental counting principle. So this is even used in criminology. Police use photographs of different facial features to help witnesses identify suspects. So one basic identification kit contains, let's see here, 195 hairlines, 99 eyes and eyebrows, 89 noses, 105 mouths, and 74 chins and cheeks. So how many different facial how many different faces can I produce? So you should get that 195 times a 99 times 89 times 105 times 74, and that is, let's see what it says. That's a pretty big number. Okay. Fundamental counting principle is basically you just multiplying each item against each other. Now, a couple of things that are kind of interesting. You know, you've got 13 billion faces that it goes through. The witness kit will go through. But what if somebody says they remember exactly the hairline and exactly the eyes and brows? Well, you don't have 195 choices or 99 choices anymore. You have 1. one choice here, one choice here. So basically, the number of faces that can be reduced down to is 691 to choose from instead of 13 billion. So that brings us to a permutation. This is very important. And a permutation is an arrangement of objects where order matters. That right there is the biggest deal for this chapter, or for this section anyways. You've got order matters. Very important. ABC is different than CBA. How many different ways can you write the letters ABC? What do you think? If you guessed 6, you're probably right. Okay, so what you could have done was said you could have gone ABC, ACB, BAC, BCA, CAB, and CBA. Those 6 different ways. In doing this, we also have something called 3. We don't really say exclamation mark. We say 3 factorial. So you would write it like this: 3 factorial is equal to 6. So what that means is this factorial means it's a decreasing element, has a decreasing element by 1. So 3 times 2 times 1. Well, 3 times 2 times 1 is 6. And this talks about our exclamation point. What does it mean? Factorials are the product of an integer and all the integers below it. So there's your decreasing factor. So if I was thinking about 4 factorial, I would start off with 4, because you always start with the number here, and then you would decrease by 1. So 4 times 3 times 2 times 1. And 4 times 3 is 12. 12 times 2 is 24. Now, it's the same type of thing if I was saying, well, any number, n. Well, the next number would be 1 less. So that would be times n minus 1. And then 1 less would be n minus 2, because it's 2 less of n. And then n minus 3, and then so on. So this is sort of a factorial formula that we're going to be using. 5 factorial, again, you start with 5. Then you decrease down 1 times 3 times 2 times 1. So that's 20. So you've got 20 times 3, which is 60, times 2, which is 120. And then 0 factorial is always 1. Okay? So a permutation, remember what did I say about permutation? Order matters. Permutation, so when you think of the word permutation, you should be thinking that order matters. That's really important. Again, a permutation is an arrangement of elements in that order matters. So like if you were trying to break open the combination of a lock, your numbers would have to be in a specific order, or you're trying to lock your lock. So in this case, you have all these different, if you only have 3 little slots here, you have all these different choices. If you just have 3 numbers, so you've got 1, 2, 3, 2, 3, 1, 1, 3, 2, 3, 2, 1, 2, 1, 3, 3, 2, 1. So again, that's 6 different choices. Well, the 6 comes from, you've got 3 choices to start with. So that's your 3 factorial, which is 3 times 2 times 1, which is 6. Okay, so again, a permutation is an arrangement of objects in specific order. Order matters. Let's consider I have 4 students walking toward their school entrance. How many different ways could they arrange themselves side by side? So 4 factorial. So that's 4 times 3 times 2 times 1. So that's going to be 12 times 2, which is 24. So if you have a whiteboard, you could try practicing with these. 6 factorial is going to be 6 times 5 times 4 times 3 times 2 times 1. So you got to work those out. And actually, if you look close enough, somewhere on your calculator, there is a calculator button that deals with just factorials. Okay, so that's something that you should look at. Familiar yourself familiarize yourself with your calculator so that you can work through those. So anyway, what is that? What's 6 times 5 times 4 times 3 times 2? So let's see if I can find the factorial. I believe it's under math, and then you look up probability. And let's see, what do we get? 720? That's what I get. Okay. Now this one here says 4 factorial, 3 factorial. So that's actually 4 times 3 times 2 times 1 times 3 times 2 times 1. So in this case, you've got 4 times 3, 12 times 2, 24 times 6. So your 24 times 6 should equal 144. Okay. This one is 10 factorial over 8 factorial. So that's 10 times 9 times 8 times 7 times 6, etc. And this one is 8 times 7 times 6 times 5. And this goes down. And all of these are going to cancel. And you end up getting 6 cancels. 7 divided by 7. 8 divided by 8. And you're left with just 10 times 9. So 10 times 9 is 90. This one, let's see. The 20 factorial is 20 times 19 times 18 times. Now, I don't really need to go any further than that because I noticed the 18 factorial at the bottom, which is going to start at 18 and go 17. And so these here will all cancel with the future ones of those. And then you have 5 factorial. So that's going to be a 5 times 4 times 3 times 2 times 1. And then I've got 5 factorial minus 3 factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1 minus 3 times 2 times 1. So 5 factorial is 20 times 6, which is 120. We already did that one. Minus 120 minus 6. So what's 120 minus 6? 114. So that's what you've got there. So basically on the top, you've got 120 and divided by 114. And let's see, I don't know, that's going to be 20 over 19. I think that reduces to 20 over 19. So as you may have guessed, there's a formula for permutations where permutations order matters. Okay. And when I'm looking for the formula, it's going to start with n over n minus r. So a lot of times it's written like this, NPR. So again, if you have n permutations of r, it's going to be n factorial over the difference of the two. So you'd say n minus r factorial. So what does that look like? It looks like if I said 5 permutations of 3, that's going to look like 5 factorial over 5 minus 3 factorial, which is 2. So what we have is, let's see if I can get that down there, 5 factorial over 2 factorial. So that's going to be, oh boy, I don't think you can see that. Let's see. Let's see if I can move this up. Here we go. Does that help? Okay, so what that's going to be is 5. Let's see, 5 times 4 times 3 times 2 times 1 over 2 times 1. 2 times 1 is going to cancel, and I just have 5 times 4, which is 20, and 20 times 3 is 60. So we just did this one. So we have 5 permutations of 3. So again, 5 factorial over 5 minus 3, parenthesis, factorial. So that becomes 5 factorial over 2 factorial. 5, 4, 3, 2, 1 cancels. 2, 1, these cancel. So I just have 20 times 3, which is 60, and that's my answer. For this one, we start off with 10 factorial, and that's over 10 minus 8, which is 2 factorial. So that actually is going to be quite a large number. You've got 10 times 9 times 8, 7, 6, 5, 4, 3, and 2's will cancel. So I'm just left with 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3. And I get, for this answer, let's see, 204, 1200. So what is that? 1, 2, 3, 2,041,200. So here's some practice problems. So you got to try to do these problems. So if you're working on these, you should pause the video so you can work on these and try to work them out. So we have 4 factorial over 4 minus 2 factorial, which becomes 2 factorial. So we go 4, 3, 2, 1 over 2, 1. These cancel. 4 times 3, 12. This one right here is 6 factorial over 6 minus 2, which is 4 factorial. So 6 times 5 times 4. Oh, that 4 will cancel with this. 4 times 3 times 2. Because this will keep going, of course, but so will that. So once you know that these cancel, just stop. And you've got 6 times 5, which is 30. Now this one is a little bit different because you've got negative 4 plus 7 permutations of 4. And so for this problem right here, you would write 7 factorial. Let's see. Here's my pen. So we're going to go minus 4, negative 4, plus 7 factorial over 3 factorial. Now that's going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is over 3 times 2 times 1. So these cancel. And you end up getting 7 times 6 times 5 times 4, which I think is 840. So we have negative 4 plus 840. And so that becomes, what, 836? Okay. This one, 5 factorial. Remember, by the way, 0 factorial is 1. Very important. This is 5 factorial over 5 minus 1, which is 4 factorial. So this is just 5 times 4 times 3, etc. And this is 4 times 3, etc. These cancel, and I just get 5, which basically means any time you have 5 permutations of 1, you're always going to get 5. In this case, this just becomes, I think, 6 factorial. So because what you have is 6 factorial over 6 minus 6. So 6 minus 6 is 0 factorial. Well, 0 factorial is 1. So you're left with whatever 6 factorial is over 1, and 6 factorial is 720. This one is saying 5 times 6 permutations of 5. So that's going to be 6 factorial over 6 minus 5, which is 1 factorial. So this is just 5 times whatever 6 factorial is, which is 5 times 720, which is 35, 3600. Oh, and this right here, I believe are the answers. So how many distinguishable ways can the letters of gun be arranged? So what if these letters repeat? What happens then? So all the examples we looked for have been arranging objects, or non-distinguishable. But what happens if we have letters repeat? So have you ever tried rewriting the letters of gun? How many ways do you think there are? There you go. Looks like 24. That's what I count. Anyway, that'll be fun. You can do that later. Okay, so for this problem right here, I want you to list all the possible permutations. So the neat thing about this, having a web video here, is that you can start and stop it. So at this point, you should stop it try to do these problems and then come back. So when you come back, what you're going to do, since you came back, is you're going to try to rewrite 1, 2, and 3 and all the different ways you can write it. So for this problem, I'm going to get 1, 2, 3, 2, 1, 3, 3, 1, 2. Let's see, 1, 3, 2. What am I missing? 2, 3, 1, and 3, 2, 1. So those are all the permutations. So there's 6 of them. But if I have T, V, W, but I only want 2 letters at a time, I'm going to have TV. I could have TW. I could have VT. I could have VW. I could have WT, and I could have WV. And then for this, taking these 2 at a time. So what is that? 1, 2, 3, 4, 5, 6. Which is 6. Again, another 3 factorial. But for this problem, if you're taking these 2 at a time, just so you know, another way of doing that is to put like a little slash there. So the first choice you have, how many choices do you have for the first problem? You got 3. And then for the second one, you have 2. So you can, that's another way of doing it. So you have a happy face, a sun, a heart, and a triangle. So you just have to rewrite all the different ways you can do that. And lastly, how many times can you rearrange A, B, C, D? See, 1, 2, 3, 4, 1, 2, 3, 6, 6 times 4, 24. I get 24. Okay. Oh, there's your solutions. Okay. These ones are the unique permutations. So these are kind of cool, actually. How many ways can I write the word design? So we've got 1, 2, 3, 4, 5, 6. So this is going to be 6 factorial. Okay. So for this problem right here, for 6 factorial, that's just 720. We've been doing that problem a couple times now. So I have 620 different ways that I can rewrite the word design. And for math, that's just 4 factorial, which is 24. 4 times 3, 4 times 3 times 2 times 1. Now, this is where it gets kind of tricky because we have 1, 2, 3, 4, 5, 6 letters in the word cheese. So it's going to start off with 6 factorial. But we're dividing out letters that are repeating. So when I do that, how many repeaters do I have? I've got 1, 2, 3 E's. So I'm going to divide this out by 3 factorial. So I'm going to go 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. So these actually cancel out. And I'm just left with 6 times 5 times 4. So 6 times 5 times 4 is 120. Then you have ballistics. So how many different letters in the word ballistic? Let's see here. 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10. And then how many different repeaters do I have? So it looks like I have 2 L's, 2 I's, and 2 S's. So this is going to be 10 factorial divided by 2 times 2 times 2. So, I mean, there's a couple ways to do that, but if you don't have a calculator, 5, 4, 3, 2, 1. I mean, there's a couple different ways you could do it, and you can just like knock off the 2's here. So you can do 2 goes into 8 4 times, 2 goes into 6 3 times, 2 goes into 4 twice. So you've got 10 times 9 times 4 times 7 times 3 times 5 times 2 times 3 times 2 times 1. That's a large number. I'll get you the answer in a minute. For the word further, we have 1, 2, 3, 4, 5, 6, 7. So we have 7 factorial over all of my repeaters. So it looks like I have 2 R's. I think that's it. So we have 7 times 6 times 5 times 4 times 3 times 2. 2's are going to cancel. So I have whatever 7 times 6 times 5 times 4 times 3 is, and I believe that's 2,520. Write a word for which there are 30 unique permutations. This one, I think I ended up, it's like loyal. Anyway, I don't remember the word. We'll get to that. And then this one, again, a permutation, x factorial over x minus the second term. So like if this was 4 permutations of 3, remember that would have been 4 factorial over 4 minus 3 factorial. So this is x factorial over parenthesis x minus parenthesis x minus 2 factorial. And so when it's all said and done, you're going to get this design 720. You've got ballistics had 453,000. This was our word level, etc. So you can check your answers online. So if I have 12 players on a softball team, how many different batting orders can be formed? So this is a permutation. Why is it a permutation? Mostly because order matters in a softball team. It's like you have to select the pitcher first, then you have the first baseman, then you have the second baseman. So if order matters, you're going to use a permutation. So we're going to go 12 permutations of 9. So how many different ways can I change my batting order? Order matters. So that's going to be 12 factorial over 12 minus 9 factorial. So that's going to be 12 times 11 times 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And this is all over 3 factorial. Well, that's going to cancel with that. And so the total batting order for this problem is actually, I don't know, I have to multiply this out. So we're going to go 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. So this number, I have different choices. I've got 7, 9, 8, 3, 3, 6, 0, 0. So I have 79 million different ways that I could actually select my batting order for my baseball players if I have 12 players on a team or softball. If I have 35 combinations on my lock, how many different ways can I choose these? Does this order matters? The order, of course, matters on a lock. So the first thing we're going to do is we're going to go 35 permutations of 3 because order matters. So this is going to be equal to 35 factorial over 35 factorial, or 35 minus 3 factorial. So if I start off going 35 times 34 times 33 times 32, etc., I don't need to keep going that far because this right here is going to become 32 factorial. And so that means that everything below 32 is going to cancel with everything up here and make 1. So my final answer will just be 35 times 34 times 33. And that's going to be, let's see, what is it? 39,270 different locker combinations for 35 different numbers that are on the lock. That's kind of neat. So we're talking about permutations right now. Mississippi, that's a really fun word to try to work through. So how many letters are in the word Mississippi? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it looks like we have 11 factorial. But we have so many repeaters. We have 1 M, We have 1, 2, 3, 4 S's. We have 1, 2, 3, 4 I's. Is that it? Well, we have 2 P's. Now I think that's it. So in doing this, we're actually going 11 times 10 times 9, 8, 7, 6, 5. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And this is all over a 4, 3, 2, 1, another 4, 3, 2, 1, and a 2, 1. So let's see, my 4, 3, 2, 1, that's gone. Let's see, 2 goes into 6 3 times. We've got a, what do we have here? We can go 8, which is 4 times 2. So 8's gone. We have a 3 that I can cancel out with this 3 right here. So that's gone. So ultimately, I've got 11 times 90 times 7 times 5, which is 35. And so how many different ways can I write the letter from the word Mississippi? I can write it 34,650 ways. Excuse me, that's pretty cool. All right. So what if order didn't matter? If order didn't matter, then how many different ways can I create a pizza if I have a list of 20 toppings or 20 items to choose from, but 3 toppings? So is this a permutation or is this a combination? So basically at this point, we have to decide, what if order didn't matter? Then I'd actually have 20 combinations of 3 and not 20 permutations of 3. And we use this when order doesn't matter. We use what's called a combination. And they're slightly different in that now we have combinations. Order doesn't matter. It doesn't matter what order you do the Rubik's Cube, right? Just as long as you get all the colors together. Anyway, this is our combination formula. So let me move this up a little bit. And so for our combination formula, this can actually be rewritten 2 different ways. So you've got, this is how we usually write it. But this right here is also another way of writing it. And so different textbooks use different ways to write it. So our textbook actually uses this way. But other textbooks use this. So it just depends, what book you're using. So what does this mean? N factorial over n minus r factorial. So this is the same thing as a permutation, but times this letter again. So be careful with that. I'm going to show you 2 different ways. This is just n over k. They're going to write it like that, but you still have to solve it like that. So if I had 5 combinations of 3, that's going to look like 5 factorial over 5 minus 3, which is 2. And then this r is whatever this number is here. So that's your 3. So that's going to be 3 factorial. So this is going to be 5 factorial. So 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. Well, these are going to cancel out and make 1. 2 is going to divide into 4, which is 2. 5 times 2, which is 10. So I have 10 different combinations. This is where order doesn't matter. C or NCR means a combination of n objects taking r at a time. So combinations, again, are arrangements when order does not matter. So ABC is not different than CBA because order doesn't matter. So if you were sitting around a group of people, you could try to brainstorm maybe 5 examples of real life combinations in 1 minute. So watching the video, you should turn it off for a second or pause it and then try to come up with 5 examples of actual combinations that you can think of. So the 5 that I came up with were pizza, and because I'm hungry, and let's see, pizza, lottery numbers, list of friends in Facebook, adding ingredients to a blender, and books on a shelf. So again, here's our number. We just did this one, 5 combinations of 3. So again, let's see if you can remember the formula. So it's going to be 5 factorial over 5 minus 3. So this is 5 minus 3 factorial, which is 2 factorial. So this is that. And then the 3 is the leftover. So that's 3. So you've got 5 times 4 times 3 times 2 times 1. 2 times 1, that's your 2 factorial, times 3 times 2 times 1. So these are going to cancel and make 1. 2 is going to go divide into 4 and make 2. 5 times 2 is 10. Okay. This one, let's do this one. So we've got 4 factorial over 4 minus 4 factorial times 4 factorial. Well, that's going to be 4 times 3 times 2 times 1. This is 0 factorial, which is 1. And then 4 times 3 times 2 times 1. These are going to cancel with these and make 1. So I could have just canceled them out right here and had 1 over 1, which is 1. So anytime you see the same numbers here and here, that's going to equal 1. And another thing, this number here, your 5, is always bigger than your number 3. So those two numbers are always going to be bigger, meaning like I would say 9 combinations of 7. I would never say 7 combinations of 9. You're not going to do that. This is the same thing as writing. So again, like I was saying before, these are different books. Textbooks have different arrangements. So this would be 7 combinations of 2. This would be 6 combinations of 4. And this would be n combinations of 2. And I do want to stress that you still have to work these out, and especially this one. This is kind of tricky. But permutations are not written like this. Only combinations are written like this. So you don't have to worry about getting those confused. So you have 7 factorial over 7 minus 2, which is 5 factorial, 2 factorial. So that's 7 times 6 times 5. And so I'm actually going to stop here because I know that this 5 is going to cancel up here. These are going to cancel and they just keep going down. And then you have times 2 times 1. 2 is going to divide into 6 3 times. So my answer is 7 times 3, which is 21. Okay, and then you've got, let's see, 6 factorial over 6 minus 4 factorial, which is 2 factorial, and you've got your 4 factorial. So you go 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 4 times 3 times 2 times 1. These are going to cancel and make 1. 2 is going to cancel into 6 and make 3. 3 times 5, 15. And lastly, you've got this right here, which is a little bit tricky because you've got n factorial over n minus 2 factorial times 2 factorial. And so let me show you how this works. So this is, remember, factorials are just decreasing by 1 each time. So this will be n times n minus 1, and then n minus 2, and then n minus 3, and keep going. Now this one starts off with n minus 2, but then the next one will be n minus 3, and so on. And then you've got 2 times 1. So what you see here is the n minus 2, n minus 3 that keeps going is going to cancel with that keeps going. So those are just 1. So it looks like what I'm finally left with is going to be n times n minus 1 all over 2. And that's that solution to this problem here. So what do you think is bigger, a permutation or a combination? Which one? We did 5 permutations of 3, and we also did 5 combinations of 3. Well, 5 permutations, so remember 5 factorial over 5 minus 3, which is 2 factorial. So we had 5 times 4 times 3 times 2 times 1 over 2 times 1. So these cancel with those. We've got 20 times 3, 60 different choices. This one looks like we had 5 factorial over 5 minus 3, it's at 2 factorial, times 3 factorial. So that's going to be 5, 4, 3, 2, 1. 2 times 1, 3 times 2 times 1. These cancel. And those are just, each one can cancel 2. You've got 2 goes into 4 twice. 5 times 2, 10. Permutation is going to have way more than a combination every time because order matters, where combinations don't. It doesn't matter for a combination. So, for example, like with T-shirts, how many different ways can you wear the T-shirts? Well, it's very specific, and order for permutations, order matters. So for these ones right here, order matters. And that's a big deal. Is this a permutation or a combination? So if you guessed permutation, you're right, because order matters. Here, I'm not sure, this might be a bad example because I'm not sure how many of you actually play the Super Lotto. But what you do need to know is that you are selecting all these numbers and they're randomly chosen. Order does not matter. Okay. So Gun High School has 120 staff members. And a committee of 8 people have to be created probably to work on our schedule. How many possible committees can be created? Order doesn't matter. We don't care about the order. So what we have is you would write this like this, 120 combinations of 8. And so you would solve that and you'd go 120 factorial over 100. So this is going to be 120 minus 8 parentheses factorial. And then you're going to have 8 factorial here. But for this case, of the 8 people that you choose, and you can solve this, you can work that out. Of the 8 people in your committee, there's a president, a vice president, and a treasurer. So how many ways can these committee members fit into these positions? You only have 3 positions for the 8 people. So I'm going to choose, I have 8 choices for the first one, and times. And then the next time I have 7 choices. And then the next time I have 3 choices. Oops, excuse me. 8, 7, 6. Sorry. Okay. And so let's see here. 8 times 7 times 6. What is that? 336. So you have 336 choices to choose between the president, vice president, and the treasurer. So here we go with 5-card draw. How many different ways can you choose 5 cards from 52? Does order matter? No. So you've got 52 combinations of 5. So when writing that, you're going to say 52 factorial over 52 minus 5 factorial times 5 factorial. See if you can actually figure out the spot on your calculator that would make this work. This isn't terrible because see the 52 minus 5, that's going to end up canceling down here later. But anyway, you can work this out. Try to verify this on your calculator. And right now, your job is to do the permutation and combination worksheet that will be passed out to you momentarily. So thanks, and I'll see you guys on Monday. All right? See you soon. Bye.